And so our next speaker is Henning Schloemer from the many-body theory group at LMU in Munich. So it's about high-temperature superconductivity and optical lattices. So I guess it stays in the topic, but from the theory side.
That's right.
So looking forward to the talk.
Okay, yeah, hi everybody. Thanks for having me and for coming to my talk. So Markus already gave a phenomenal introduction to Fermi-Hubbard physics and optical lattices and so on. And today I want to focus on more the high temperature superconducting side and really talk about how we can make progress towards measuring these very interesting phases of matter here. And I want to give, because Markus already introduced this very nicely, kind of a different perspective to the challenges that arise and maybe kind of draw some sort of roadmap, if you wish. So actually already very early on in the field, so in 2002, which is, by the way, the same year that this mod insulator to superfluid paper came out that Markus also showed, this kind of vision was introduced that if you have inherently repulsively interacting fermions and you put them into an optical lattice, you want to study how they basically form a superfluid in a superconductor. And now there has been a lot of progress in this direction, starting with creating mod insulating states that have kind of longer and longer range antiferromagnetic order, and then also doped systems. Right, so this is the same plot that you saw earlier. And now, the big open questions for the next years are really, can we understand microscopically the origin of the pseudogap, where we saw some very exciting advancements right now? And then also, of course, can we measure and prepare these collectively ordered states, so in particular stripe phases, charge density wave order, and also superconductivity. Of course, ultimately all in order to understand better strongly correlated materials such as cuprates, where we basically model these systems by these minimal kind of single band strongly correlated systems, and then we want to understand them. Okay, so looking again here at this plain vanilla Fermi-Hubbard model, what are really the big challenges in order to realize these kind of low energy states? And the first one, Markus introduces, is state preparation. So you need to go to extremely low temperatures in order to actually realize these type of states. And in particular, kind of inherent to the Fermi-Hubbard model, there's a different problem, which is that, in fact, you do not get any long-range superconducting order if you do not have next to nearest neighbor hopping terms in the Hamiltonian. So the ground state is super fragile in that sense. There's stripes, there's superconductivity, everything fluctuates a lot, and so on. So this is certainly very challenging. Of course, if we look at this plot here, we really need to take into account these new experiments that Markus introduced, where we have really super low temperatures, and we can start to dope these systems and then see what happens, and analyze pseudogap physics and charge density waves and so on. Now, what's the second challenge, in particular with regard to measuring superconductivity? Now, even if we can prepare a state that has kind of long-range coherence, how do we measure it? So usually, if you have some, let's say, attractively interacting fermionic system, here for simplicity, let's say we have some BEC type of system. What we can do is release the atoms from the trap. They will travel, and then you take a snapshot after some time, and then you will essentially find what momentum distribution these atoms were in. However, now in our case, this pairing is very complicated. It's kind of inherent to the lattice physics. So if we turn off the lattice and release them from the trap, what happens is that the atoms just go anywhere, right? So this is going to be very, very challenging to do kind of time of flight measurements here. Okay, so let's focus here on the first challenge again. Instead of going down in temperature, how about we try to do something else, which is if we have some kind of temperature regime which is easily accessible, can we sort of find models that are interesting and have energy scales that are much higher? So something that we can access with kind of current state-of-the-art technology. And I want to mention that this has already been successful in an exciting collaboration with Emanuel Bloch over at MPQ, where we basically realized a mixed-dimensional Fermi-Hubbard model. So you can imagine you have some sort of potential tilt in the system, and then you freeze the dynamics of the atoms in one direction. And basically what that does is it heavily favors the formation of charge density wave and stripes, right? So you can imagine if you have two holes sitting on top of each other, if they cannot hop in that direction, there will be basically no Pauli repulsion. So then you will favor kind of the formation of these stripes. And also here on this right-hand side, you can see a snapshot where you really find these holes like to kind of align along a single line. Now, there's many sort of observables that you can look at. I will only skip over this very briefly, but this is all kind of consistent with the formation of fluctuating stripes, where you have a domain wall of the antiferromagnet in the background at this kind of line of holes that aligns. All right, so how about superconductivity? Are there also systems that we can study which have kind of enhanced energy scales for superconductivity? And so this brings me to the discovery of bilayer nickelates, which is a very exciting kind of new class of materials that have been discovered roughly 2 years ago, which are very similar in their atomic and also electronic structure to cuprates. So nickel is right next to copper in the periodic table. And the basic structure is very similar. You have, in this case, you have kind of 2 layers of nickel oxide planes. And then what happens when you introduce some pressure is that these orbitals along the vertical direction will align. And when this happens, these are like actual measurements in the material, you will find that above a certain pressure threshold, you will have a superconducting phase of matter. And now, if you look at the DFT calculations, constrained RPA, and so on, you can kind of cook up some minimalistic models similar to the Fermi-Hubbard model. And if you write down such a single band model, it would be the following. So we have now 2 layers of Fermi-Hubbard type systems, and the atoms only hop within each plane. So this is what you kind of get from the DFT. However, there will be some magnetic exchange in the vertical direction. So there's still going to be some super exchange happening. And of course, also super exchange kind of within the plane. We've looked at this model here using large-scale numerics and find a very interesting phase diagram where, let's say, we start here on the left-hand side in this plot. We have a very strong J-perp. So you imagine, you have these atoms sitting on these different layers, and they form basically a very tightly bound singlet. Now, these singlets are basically bosons. They can hop around perturbatively and then condense, giving you this BEC kind of phase. And then if you increase your T-parallel, these pairs will basically delocalize more and more and then basically form some BCS type of phase. So this is already very interesting because this BEC to BCS crossover is very well studied in ultra-cold atoms, however, kind of on the attractive side, right? So now we also see this kind of phenomenology in repulsively interacting fermions. But the most striking feature of this phase diagram is the critical temperatures. So what we expect is actually critical temperatures of the regime of J-perp itself, which is really huge and something we can kind of routinely now achieve in ultra-cold atoms. So this is kind of a natural platform, these bilayer systems, to study basically states that have coherent long-range order. Long-range pairing order at current temperatures. And I want to mention that this type of system has already been studied in ultra-cold atom experiments in some sort of ladder geometry. So here you also have this mixed dimensional setting, so holes can only hop in one direction. And then you will see, kind of in real space images, that these holes would like to sit on top of each other, essentially. So now imagine we have an actual 2D system. Now we have a finite critical temperature where we have this BKT transition to a superconductor. And now the big question is, how do we actually measure it? So that's challenge number 2. And what's the challenge here? So imagine we create a very fragile kind of superposition of these Fock states in our quantum gas simulator. And now we need to somehow define an experimental operation which basically picks out, let's say, a pair of atoms here and then essentially adds a singlet to them coherently. Right? And that's super hard to do because maybe you can remove some particles, you can add some particles, but doing this in a coherent fashion is going to be extremely challenging. And so what we propose now, especially in the context of these bilayer systems, is to use the particle-hole symmetry of the square lattice Fermi-Hubbard model. So that's basically telling you that whether you doublon dope the model or you hole dope the model is the same. So it gives you exactly the same physics. So what you can do now is imagine a situation where you have this bilayer. You want to hole dope it because that's what you have in the actual materials. But now instead what you do, you actually doublon dope the lower layer and you hole dope the upper layer. This is equivalent, up to some kind of subtleties, which you can read about in our publication. But that's essentially equivalent to having a fully hole-doped system. And now, it's instructive to kind of look at this conversion table here, where in the transformed basis, which is what we would like to kind of simulate, let's say we have a hole-hole pair. Now, in this partial particle-hole transform basis, which is what we physically implement, this corresponds exactly to a doublon hole pair, right? So doublon on the lower layer and a hole in the upper layer. The singlet stays the same, so this is invariant under this transformation. And now, importantly, the pair creation operator, delta dagger, which kind of creates a singlet, is going to be represented in this physical basis simply by a hopping term. So all you need to do in order to basically create a singlet is make one of these particles from the doublon in the lower layer hop to the upper layer, and then in this transformed basis you have created coherently a particle pair. All right, so going actually to state preparation schemes, this mixed dimensional setting you can nicely realize by applying potential gradients to these two different layers. So that basically makes tunneling between the two layers off resonant, right? And so then you have on intermediate time scales this mixed dimensional setting. So this is depicted here as well in this scheme. Basically, the left double well side is the lower one, and the right one, so it's the other way around. So the energetically upper one is the left one, and the energetically lower one is the right one. And so, what we can do now is basically do a trick where we make hopping resonant again. So if we choose delta, which is the energy difference between the two sides, to be exactly the same as the on-site interaction U, what will happen is that we will drive coherent oscillations between the singlet pair on the left-hand side and the doublon hole pair on the right-hand side. And this is exactly what we can use in order to measure now these pair-pair correlations, which I will go into in a bit more detail later. But for extra state preparation, what we propose is to start in a band insulator in the lower layer, which we can now get with extremely low entropy, as Markus introduced. And in the upper layer, we basically just have an empty optical lattice. And now, in order to dope the system, we can basically use already this type of oscillation. So we make this tunneling resonant for a certain amount of time. We create a superposition between doublon hole pairs and singlets with some weights on every side, and that would basically give us some grand canonical ensemble of a doped system in that sense. And then we can adiabatically turn on the hopping in the planes and basically tune the system into the low energy state of our target Hamiltonian, which these are numerical calculations now, which basically have algebraic decay. There's a log plot, so they have algebraic decay of these pair-pair correlations. Okay, so how do we actually access these correlations now? That's the next big question. And for this, it's very intuitive to kind of go to the strongly coupled limit, where we have J-perp much, much stronger than the hopping T. And in this case, our Hilbert space only consists of basically singlets and whole-hole pairs. Okay, so let's say we have some state like this, which by definition has kind of coherent pairing correlations between two different sides. So we have an equal superposition of doublon hole pairs and singlets on each side. Which basically corresponds in sort of a Bloch sphere language. If you imagine my whole pair is the upper part and the singlet is the lower part, corresponds just to some vector in the equatorial plane. And now we want to access these coherent correlations. So what we can do is we can make a pi-half tunneling pulse, exactly using this resonance condition that I showed earlier. And that will basically simply rotate this state into the singlet. So now my state looks like that. And now I can actually make measurements diagonally in my Fock basis and just check where I have a singlet and where I don't have a singlet. And then my coherent pair-pair correlations exactly corresponds to density-density correlations in my physical system. Okay, so after state preparation, you can freeze in-plane dynamics, so you ramp up your lattice depth. You then do this pi-half globally. Basically, you apply this pi-half basis rotation pulse. And then you measure in the Fock basis and basically evaluate here this correlator, which is then quite straightforward. Now, of course, if you go away from this perturbative limit, there will be other states in your Hilbert space. You will also have something where you have a particle in the lower layer and maybe a hole in the upper layer. But it turns out that this resonant kind of tunneling pulse that we do is only resonant within the subspace. So basically, all of the other states are left invariant, and things turn out to be OK. Okay, so kind of to summarize this part here, we have a state preparation, which we can nicely do in these bilayer systems because they feature extremely high critical temperatures for an S-wave superconductor in this case. And then we can use this measurement scheme and rotate basically the bases between doublon hole pairs and singlets in order to measure these coherences. So that really kind of opens a new chapter towards studying high TC compounds, in this case, bilayer nickelates, at currently available temperatures and with current techniques. So this is something we can really do in the very, very near term. So I do want to mention that we also have proposals to study D-wave superconducting correlations in the two-dimensional Fermi-Hubbard model. And so this basically uses the repulsive attractive mapping of the Fermi-Hubbard model, and you also do some partial particle hole transformation. So Daniel, who's also here in the audience, also developed a very general framework for this. So that's this other reference here. I'm not going to go into details here, but the general idea is that if you have superlattice control in 2 dimensions, so let's say you can tune your double wells independently in x and y directions, and you do have access to a few gates, right? So this is really just 4 gates here that we apply. We have some pi-half tunneling pulse, which we can do. We basically need some local control of the spins, so if we can locally flip the spins, and then we can apply magnetic fields adiabatically. This will basically allow us in some Ramsey kind of type fashion to access these D-wave pair-pair correlations also in the 2D Fermi-Hubbard model, which at these temperatures will certainly be short range, but nevertheless we can study them and compare them to S-wave and so on and make progress here. All right, so going back here to this kind of vision and roadmap, I fully agree with Markus that this is really an exciting time in the field of analog quantum simulation, where we can start to study these super enigmatic kind of phases of matter, including kind of collective charge and spin order, as well as superconductivity, and also, as Markus introduced, the pseudogap. So here I want to also advertise another proposal that we had recently, which basically describes the pseudogap. It's somewhere between the stripe picture and the spin liquid picture, where the basic idea is that you have these stripes, right, which form kind of, they break the C4 symmetry. And now what happens basically when they melt away, one possible scenario is that they form these kind of fluctuating domain walls. And we show that under certain assumptions, these fluctuating domain walls can give rise to a topologically non-trivial phase of matter, which can then allow for some of the enigmatic features that you see in the pseudogap, such as a small Fermi surface, although you don't have any visible symmetry breaking. All right, so let me kind of summarize here and thank all of my collaborators, Fabian, Annabelle, and Hannah from LMU, and then the whole lithium team from MPQ for many exciting collaborations here. And then lastly, kind of say and finish by appreciating this large potential that we now have using maybe hybrid analog-digital techniques. So we prepare a state using analog techniques, and then we can do additional measurements and so on, and kind of modify the state using some small, very short circuit using digital techniques. Okay, so that's all I want to say. I'm happy to take any questions and discuss.
Thanks a lot, Henning. Questions?